Hello, I'm Randy, and this lecture is going to be a pretty short one on function binding. I originally learned all of my reflection and introspection stuff from a guy named John Edwards and some DigiPen students, but mostly that guy. He made a really cool video. He came to DigiPen. He works at that game company in 2010 or so. He did a really long, 2-hour talk on introspection, and I have the video, but it's too big to fit on Moodle, and I always offer to give it to anybody if they just email me and ask for it. So if you want to see the video of his stuff, just ask for it, and I can send it to you. So here's a quick overview of all the things in this lecture. The most important ones here are the first 3 lines, and then the rest is just sort of talking about the first 3. So we're going to start off with a little bit about what introspection is and how to do it. So when you're compiling your code, the compiler knows a lot about the types of your data, and after you compile your code, all this information is lost. And a lot of languages give you access to this information about what types are things and their names and sizes and what they inherit from, accessible from runtime. But if you want to do this in C++, you have to make your own custom code to do this. And the idea of introspection is that you take that data that's known at compile time and you store it somewhere so that way you can access it during runtime. And this lets you write code that is aware of the type of data it's messing with. So then you can write really generic code, and you can be super time efficient, as a programmer. So there's a lot of questions that can arise when you make a big project, especially if you're dealing with editors and stuff, where you deal with a lot of different types of data. But every time you want to support a new type of data, you don't want to write more code. These are the types of questions that arise in that situation. And introspection can answer these. For example, while your program is running, what if you want to know what sort of methods a class has? Or how can I send this specific type to a script, or bring it from script back to C++. All of these can be automated and answered by an introspection implementation. So in order to have this data from compile time available during runtime, you have to store it somewhere. So you're going to store it in some tables. This is most of the information that you would want to know about a type. You want to have a string representation of its name, its size, what data members it has, what methods, if any, what it inherits from, if it inherits from anything or not. And in order to store this information, you could just use a really simple struct. And there you go. All that information can be stored in that thing. And then you can keep track of all these type information structs. You have one of these for each type of thing that you want to deal with. A type info struct for an integer, one for float, one for double, one for a structure, one for a class, and so on and so forth. So in order to get that information in that struct, you're going to need a little bit of code to do that. And this is called registering your data. So you have to register this data in these structs and store it. This is what you want your code to look like when you're registering data. Something extremely simple, very intuitive. I think if you read this, you would all know sort of what this is doing. This is registering information about an int. This is registering some information about a struct. The things these will store are name, size, and that's actually about it, name and size. It'll create that struct and that table for you. And then this is filling out the specific portion of that struct for what data members does this have. This sticks data member X, which could be an int or whatever. It'll detect that it's an int and put it in that type info struct for you, the type info of this type right here. So when you're making an introspection API, and by API I mean mostly these macros, you want to hide all this really crazy, ugly template stuff so that people just use this really nice, simple thing. People shouldn't have to know how your introspection works to use it. Therefore, macros. assuming this is where you're storing all your introspection data, and you can get it somehow, perhaps this is like a singleton thing, where you get a pointer to your introspection tables. You have a templated function called registers type, so where you can pass in the type here, and do whatever you want inside this. But most importantly, when you start writing your code, you're going to want those two, the stringize and the size of. So real quick, in case you don't know how stringize works, inside of a macro, this pound sign here will turn whatever text it was in place of t into a string and just like wrap it in quotations. So now suddenly, if I pass in int, I would all at once have the size of int and a string saying just int for like later use during runtime. I can look that up whenever I want. So here's a little bit of code demonstrating this thing. Just to be clear, I took manager out of this name to make it shorter. Here's like a really simple way to implement a singleton of a type. You can make the constructor and destructor private, and you only expose this get function. Then you construct static instance inside the get function, which is only constructed one time, the first time it's called, and then you just always return a pointer to it. So that's what that get thing was. And this is what register type might look like. You can see that the type info struct is static as well. So you get one of these type info structs for each type passed in as a template type. And then after you construct a type info struct, you put in data, like any data that you want to know about a type in there. And then, of course, you'll probably want to have a hash table of strings to these type info structs. So that way, if you're reading a file and you read like int, float, double, you can use these strings to look up these structs and immediately know everything about that type from a string. That's really important for like serialization and whatnot, and data driving things. This slide is just like talking a little bit more specifically about these two lines here. You're going to probably want to put these two lines in like a nice own specific function. That way, you can also look up a type info struct through a template parameter. You can probably make a nice macro for this so that people can get the type info of a type by just typing int inside of the parentheses there. And then here's like a bunch more macros that you'll probably end up making or something to this effect. So whenever you register some type, there's a bunch of different ways you can retrieve it. You can retrieve it by a template type, by passing in an actual object, and then you just use decal type on it, which then uses this one. You can look up a type by a string. You can get the type of a member using like a little bit of template metaprogramming or whatever have you. And then, of course, you can like set information about how to serialize a type or read it in from a file or a whole, like anything really. The sky's the limit here. This is just like the API you use to like deal with introspection. Okay, so that's the basic idea of like setting up introspection in C++. You register some data and then you look it up later, and it can be really useful. One way this information is useful is to make a variable. And when I say variable, I mean a small class or struct that knows how to contain anything that has been registered in introspection. So say we have one of these variables, like so. We can assign it to an integer. Once we do that, it is holding that, like it's holding a pointer to this integer inside of it. And then we can also send it to Lua, the integer itself, serialize it. And I'm just demonstrating like you can also assign this variable to like structures or anything in C++ that's been registered. You want to be able to assign to this variable so you can write generic code. So the implementation of the variable is really, really simple. You have type info and a void pointer. void pointer points to your object, type info describes what's in the void pointer. So when you're assigning to a variable, take the address of whatever you're assigning to and store it, and then you look up the type info of it and store that. And then when you want to get this data out of the void pointer, you can make a really small generic cast function. I call it getValue because it gets the value of what's in the void pointer. So you tell getValue what type you want to interpret the void pointer as, typecast it to that type of pointer, and then dereference it. Super simple. And that's really about all there is to the variable, but it's one of the most useful things that you can make. And it lets you do function binding, which is this is how I've been leading up to function binding. So let's create a generic function. This generic function will bind any function so that we can just use the overload call operator on this guy, and it'll call our function for us. This will let us write code that can call anything in C++, which is, I don't know. You can imagine it's really useful, but I have some slides dedicated to describing why this is useful for later. So just trust me that this is a very useful thing. And then if you want to pass in arguments to your function, you can use these variables that we just talked about. So step 1 of function binding, create a generic function. The easiest way to do this is to have your function pointer as a constant that's passed into a template parameter. So here, this right here would describe the type of your function. Here's the type of the function. This is a constant template parameter of that exact function pointer. And then this right here, build function, is just a really simple C-style static function, and it returns our generic object. However, the inside code isn't finished yet. I just want to describe that the pointer itself is passed in as a template parameter. And I'll show exactly how to use this in a moment. So now I filled in the inside of this. The function itself, this is our generic object. It's actually, a problem with this is being able to call your function pointer, and an easy way to allow your generic object to call this function pointer is to have a helper that calls the function pointer. So you give it an address of a helper. This helper is just another C function. But you forward these types to the helper. So now whenever your function has the call operator executed, it just invokes this call function pointer here. It has information about the function pointer type, and it calls that function pointer that is a template parameter. So you forward the type to, I'm going to go through the flow of this. So I went back a couple slides. You call build function. You pass in your function here and here as template parameters. Those get forwarded to the helper. The helper is given to the function. When the function is called with the call operator, it calls the helper. And then the helper finally calls the actual function pointer. So this sounds a little convoluted, a few hoops to jump through to call this one function pointer here. However, this is all forwarded through templates, meaning it's forwarded at compile time. And the compiler is definitely smart enough to compile away these little steps that you have to go through, so that it'll actually boil down to just one function call. Because it knows that this is known at compile time, this is known at compile time, so those intermediate steps are really just steps telling the compiler how to finally call this. And it can get rid of all that boilerplate for you, and it'll be really efficient. So this demo, these last 3 slides, this example, is showing how to build a function for a void pointer or a function that returns nothing and takes no arguments. I don't know if you caught that. I'll back up a slide. Here's the pointer itself being passed in. You can see that it doesn't take anything, it doesn't return anything. So then when you call this function pointer, there's no arguments or anything, it doesn't return anything. And then we can assert that our argument count that we've been passed in is 0 as well. However, like this is how it works for something that doesn't take arguments, like so. So this is how you actually use all this stuff. Here's the original build function. The function pointer type, the function pointer itself as a constant, and then the function pointer passed in as an argument for deducing. This is actually passed in here to deduce the argument types, but since there's no arguments, it looks a little redundant. And then that's how you call this thing. So all that ugly code inside that might be a little confusing, you can study this, and like I'll have example code showing how it works. But really the whole point is just to make something that's really simple. Like this right here, that's really simple. That's what we want. So here's a little bit of code showing how to actually handle arguments. Here's our same build function, except now it makes sense as to why I'm passing in the function pointer here, because we can have a template argument describing, or a template parameter describing the type of the argument passed in. And then here's the call helper. Call helper overload will also be able to take in another template parameter for an argument. And here's the final call helper. And this is the really cool part. Here's this argument that was forwarded. Now you can use it on get value. And this is going to interpret the first argument as that template type. And like this right here is the magic of how to bind any function in C or any function in C++. And then I didn't actually talk about the signature, but that's just like a little bit of implementation detail that'll be in the demo. So I showed how to do a void return, no argument function pointer, void return, one argument. So what if you wanted more of them? Then you'll have to make a lot more overloads, a lot of them. And then what if you want to have a non-void return? You want to actually return something. Well, you can hold the return value in a variable, but you have to make more overloads to actually support like the template type with a return value. And here's a quick screenshot of my function header. This is like 1/10 of the file, so it goes like way up and down. And if you actually support all the overloads for const, non-const methods, const, non-const, void, and non-void return, and then like all the like permutations in between, then yeah, you'll have a lot of lines of code. But the demo code that I'll post online is really short. It's like 100. Okay, so is there any questions about like this uglier template code? Because that was the only hard part. The rest of this from here on is pretty simple. Cool. I didn't think there'd be any questions because demo code will answer them for you. So let's just talk about how this thing is useful. So we have a generic function. Cool. Now what? Well, this is what. Have you ever seen a property grid inside of an editor? You probably have, and you probably thought they'd be hard to code, or at least very time consuming. Imagine having to by hand add like all of these things that accept values input and like set them. Ugh. Doing this by hand would require an army of monkey programmers. So instead, if you have a generic function, you can create a property, which just holds a getter and setter method. So that way you can call get or call set, and suddenly you can represent all of these things really, really easily. Each of these would just have a different getter and setter associated with them to set a value or get it and show it on the screen. And suddenly this turns out to be really simple given a generic function. Another cool thing that you could do, I haven't actually seen this in a DigiPen game, but it's totally doable, is visual scripting. You can actually have these things like nodes or some sort of flow diagram, and then you can draw lines between different functions so that they call each other at different times. And you can set this up really easily just by making a generic function pointer or function object, giving it to something, and having it call it. So suddenly, like solving this sort of problem without writing an insane amount of code, becomes pretty simple if you can write more generic code. Here's another example. Say we create a function object inside of a macro. And then we have a little bit of code that allows this function object to be called from script. If we do that, then we can make a macro called register function. This means I can call this from script now. So you can call OpenGL functions in any scripting language that you have. And then suddenly, you can render a beautiful scene from script. And this is cool because usually with a lot of scripting languages, you can like hot load your file, your script file, whenever it's edited. So then you can like render different stuff, save, and then your changes will just immediately appear on screen without even recompiling or shutting your program down. And I have a demo of that, like a video to show. Another really cool usage of just the variable itself is messaging. You can make a few overloads and just send data from one place to another. And this is really type-safe stuff as well because you have type information in here. This might be implemented without introspection with like void pointers and typecasting or inheritance. But here it's a lot simpler in my opinion. And then suddenly messaging can get really cool. You can have subscriptions and posting of messages to where when you subscribe to someone, you give them a function. When they post a message of a certain type, they call your function. So now suddenly you don't have to be like, did you post this type of message? Did you post this type of message? Did you post this type of message? You could just be like, hey, tell me when you post this message so I don't sit here waiting and like asking you over and over again. So that means it's really efficient. So yeah, this is like as good as messaging gets and is really easy with a function object. And there's more uses that I don't want to put in the slides because there's other things to show. So this is a demo of doing some like live function binding and calling some stuff from Lua. And I made this sometime in my sophomore year. So it's a little old, but that's cool. So here's some functions in C++, and I can uncomment these lines to suddenly allow them to be called like from Lua. And what I'm doing is I'm writing a Lua file and saving it. Whenever it's saved, it gets this, like my program gets the update, and I'll just let you guys watch the rest. So you can imagine if this was in a game editor or you were making a game with this sort of tool, it would increase your productivity like exponentially compared to if you had to modify a text file or a C file and then recompile and then load your game up and then go to that spot in the game and then see if you can tell a difference. You can just change a number and instantly see the update with this sort of tool. So if any of you have taken CS200, I'm using my CS200 code for the graphics. Because at this time I didn't actually know how to do like my own graphics. And then of course you can bind more interesting things besides just OpenGL functions, like perhaps spawning stuff from a physics engine. So then here I just started spawning boxes. And you can see that this would, like, it's pretty clear that this would be really, really useful for making a game. So is there any questions so far from the few that are remaining?